Hi 243, in this video we're going to move into section 6.7 where we're first going to talk about binomial distributions. Geometric will be in a second video. So let's consider an example. Suppose we decide to record the gender of the next 25 newborns at a particular hospital. We want to ask the following questions. What's the chance that at least 15 of them are going to be female? What's the chance that between 10 and 15 are female? Out of the 25 newborns, how many can we expect to be female? Notice that all of these questions are talking about something that's going to be discrete, right? It's not going to be continuous because we're talking about the number of female newborns, right? Okay, so we're moving into a realm of talking about discrete random variables as opposed to continuous random variables, which is what we were doing with the standard normal distribution. So these questions here are going to be answered using a binomial distribution, which is going to be using a discrete random variable. So properties. A binomial experiment consists of a sequence of trials with the following conditions, right? So there are a fixed number of trials. We use n to denote the fixed number of trials. Each trial results in one of only two possible outcomes, labeled success or labeled failure. The term success doesn't necessarily mean something positive has happened. It just means that you have acquired a result that satisfies the question. Right? So for example, if the random variable is the number of defective items produced, then being defective is considered a success, right? So being success is dependent upon how you define your random variable, right? If your random variable is a female newborn, right, then seeing a female newborn as a result, right, of the experiment is going to, or the trial is going to be a success. Okay. Outcomes of different trials are independent, right? They're not related to each other. They don't affect each other. And the probability of success is the same for each trial. So for example, with the female newborns, right? Okay, each of the babies being born is independent of the other, right? The gender of one doesn't determine the gender of the other. And the probability of a success of a female newborn being born is the same every single time a baby is born. So the binomial random variable x is defined as the following. X is the number of successes observed when a binomial experiment is performed. So this probability distribution that we're going to produce from this random variable is called the binomial probability distribution. So let's look at the formula. It's going to be kind of crazy because what's interesting is that the standard normal distribution, we never gave it a formula. We didn't give you a rule to describe the curve thing that makes the sort of bell-shaped curve. We never gave you a function for that. We never showed you what the rule was. But with these binomial distributions, we actually are going to see an actual rule, which is kind of neat. So let's let n equal the number of independent trials in a binomial experiment. Let p equal the constant probability any particular trial results in a success. For example, the female newborns, the probability is going to be 0.5 because there is an equal probability of a girl or boy baby being born. So here's how the formula works, and it looks really scary, yikes, right? So the probability of x, right? So this is again a function notation here, and this p of x is equal to the following notation for probability, right? Probability, and that's what's right here. Let me use my mouse right there, right? So p of x, this is just function notation. This is equal to probability of x successes among the n trials, right? So for example, with the female newborn thing, probability of 10 females born among the 25 babies, right? Okay, so the 25 is going to be the total number of babies you look at. X is going to be saying, well, if there's 10 females, what's the probability of that happening? That's the idea. Okay, and it's computed using the following notation, right? If you haven't seen this in 111, this is worth noticing here. This exclamation point does not mean that you say the letter n really loud, right? You don't say n like that, right? This is a factorial symbol, right? This means that when you see a number living right here, like for example, if it said 5 factorial or 5 exclamation point, that means you do 5 times 4 times 3 times 2 times 1. Right? You just multiply all of the whole numbers starting at whatever number is given before the exclamation point. Okay, so this right here, this rule, scary looking thing, right, shows you how to compute this value for the binomial distribution, right, or the probability of, let's say, 10 females among the 25 babies. Okay, notice here x has to be a discrete value, right? It has to be 0, 1, 2, 3, all the way up to n, and it doesn't make any sense for x to be bigger than n because how can you have more successes than you tried, right? You can't have 26 baby girls born from 25 babies, right? It doesn't make any sense. Okay. So this is just an alternative way to write this expression here, but we don't have to worry about it. It's using combination notation. Okay. So, like I already said, this is a formula. So instead of using a table, we're just calculating the values for this probability distribution from a formula instead of looking it up. We'll actually see that in a second. We can use a table also. There's one in the back of your book. Okay, so let's see an example. 60% of all computers sold by a large computer retailer are laptops and 40% are desktop models. The type of computer purchased by each of the next 12 customers will be recorded. Okay, so notice there's already some numbers given in this information. Maybe one of them is a trial number, maybe one of them is a probability. We'll see how this works. So define the random variable of interest as x, which is the number of laptops purchased among these 12 customers. Okay, so again, this number can vary, right? Okay, because it can be anywhere from 0 to 12. The binomial random variable x is going to count the number of laptops purchased, right? And the purchase of a laptop is going to be considered a success, and we're going to denote that by s. So the probability distribution of x is given by, right, the following. Because notice that n, the number of trials, is 12, right? And the probability of a success is this 40%, right? Is that right? No, the desktop models are 40%. So the probability of choosing a laptop is actually 60%, right? 0.6. Okay? So down here when we write our distribution, we're going to see n factorial. That's the n right there, the number of trials, over. The reason we don't see an x here is because x is the variable, right? We don't know what that's going to be yet. We haven't calculated, for example, the probability that 5 people buy a laptop, right? That x is waiting for you to plug in a number, but we have to generate the formula first, right? Okay, so we've got n factorial over x factorial times 12, which is n, minus x factorial. And then here we have p to the x and 1 minus p to the n minus x. Okay? That's just plugging in all of that stuff from the formula on the previous slide. So let's now use it. What's the probability exactly 4 of the next 12 computers sold are laptops? That means what we're doing is plugging in 4. We're saying let x equal 4, the probability that x equals 4. This is different from a continuous random variable because remember, in a continuous one, this probability was always 0, right? Because you're saying the probability of exactly one thing happening. It's not likely. But when you have a discrete random variable, that's different because you're counting individual things, right? So this is the only way we talk about discrete random variables is with this like individual counting idea, right? You can talk about an interval, but it's still talking about, for example, an interval of 3 to 7, right? It's going to say 3, 4, 5, 6, and 7. You're still thinking of it as a discrete variable. Okay, so this is where we just plug in the numbers into the formula, right? We do n factorial over x factorial, and then this is n minus x factorial, and then we're plugging in the exponent up here. Okay, this just comes down to a little bit of arithmetic, and we're going to do an example in class to really iron out how these are working. Okay, so if many groups of 12 purchasers are examined, because remember this is in the long run, about 4.2% of them will include exactly 4 laptops. Good. So what's the probability that between 4 and 7 inclusively are laptops? Now, again, between 4 and 7 inclusively makes a difference if it's a discrete random variable versus a continuous one, because for discrete, you want to actually include 4 and 7. If it was discrete and you weren't including 4 and 7, then you wouldn't say 4 to 7, you would say 5 to 6, right? Again, it's the issue between discrete versus continuous values for the variable, okay? So here, since they're saying probability of between 4 and 7, we say we'll do 4 and 5 and 6 and 7. You're calculating each of those probabilities individually and adding them all up, right? And this is like, you have to do each of those crazy factorial formula things for each one of these things. Oh my goodness, right? Which means you have to plug in all that stuff 4 times and then get all these numbers and then ta-da, there's your number, okay? So again, this is going to become tedious, right? So there's a table actually in the back of your book, and it's actually not table 9. I believe it's actually table 6. Yeah, it's table 6. Okay, so let's see what the difference would be if you wanted to do between 4 and 7, like I said before. You would just do 5 and 6, right? So you would just have these two calculations, and you'd get a smaller probability. Okay, and I already mentioned that. So let's see how we use this table. It's again table 6, not table 9. Apologize for that. And it's actually, it starts on page 650 in your textbook. So let's use the table to find p of x for any particular value of x. So the first thing you want to do is use the table. It's separated into values for trial, right? So n equals 5, n equals 10, 15, or 20, or 25. And then once you are in the correct section for the number of trials, then you move down to the row that has your x that you're wanting to evaluate the function for, and then you will read over across to find the value for p, which remember p is probability of a success occurring. Right? So you have the necessary probability or the necessary value for the function being given by finding the correct row for x and the right column for p. Okay, just like we did with the table for z values. Okay. All right, so we don't have to do this slide. That was just a basic intro to the binomial distribution. We'll do an example when we are in class on Tuesday.